In this unit, we're going to learn about how we count atoms. And we have to count atoms because atoms are the actual pieces that play a role in chemical reactions. One atom can bond with another atom. And so we need to know how many atoms we have. And to do that, we weigh the things out and we use what's called a molar mass to figure out how many atoms we have. So there is a number called a mole, and I don't mean the ugly little underground critter that destroys yards. I mean 6.022 times 10 to the 23rd. A lot of times I'll just write 6.02 times 10 to the 23rd, depending on how much precision we need. This is 6.02 hexillion. It's a big number. Don't be afraid of it just because we write it in scientific notation. We just don't want to put 21 zeros afterwards every time because we're lazy and all those zeros are hard to count. Okay, so the mole is special because it simplifies counting atoms. If we want to count something, we need to know like how many atoms are in 1 gram. Well, it depends on the atom, so that would be different for every atom. And so every single atom, every single element has its own molar mass, or mass for 1 mole. So 1 mole of a given atom has a mass in grams equal to its atomic mass. Remember, atomic mass is the weighted average of all the different isotopes. It's the decimal point on the table. So I believe like sulfur is 32.06 AMU. That's its mass in atomic mass units. That means, it also means if we had 1 mole of sulfur atoms, if we had this many sulfur atoms, 6.02 times 10 to the 23rd sulfur atoms, it would have a mass of 32.06 grams. Okay. So sodium, another example, has a mass of 22.99 AMU. That's its atomic mass. Thus, 1 mole of sodium has a mass of 22.9 grams. So if we had 6.02 times 10 to the 23 atoms of sodium, it would have a mass of 22.99 grams. So how come equal amounts of sulfur and sodium, equal numbers of atoms, have different masses? Well, sulfur atoms are bigger. There's more protons and neutrons in the nucleus, so the atoms have more mass, so 1 mole of them has more mass. The mass of 1 mole is called molar mass and has units grams per mole. So 32.06 atomic mass units is the atomic mass of sulfur, but it's also 32.06 grams for every mole of sulfur atoms. And that's the reason this number was picked. Anytime you have a mole of atoms, the mass of that mole has a mass equal to the molar mass of the element, or the atomic mass of the element. So if we know the molar mass of an object, we can determine how many atoms are present because we can use the conversion factor that molar mass lets us convert from moles to grams, and since we know a mole is just 6.02 times 10 to the 23rd things, that lets us to actually convert to atoms as well. Now, when we have compounds, we have to deal with this a little bit differently, but let's think about why we count atoms in the first place. If we want to make the compound sodium chloride, which is just table salt, we need 1 atom of sodium for every single atom of chlorine. That's not the same as 1 gram of sodium for 1 gram of chlorine. Remember, gram is the amount of matter. And since sodium atoms are smaller, 1 gram of them is going to have more atoms than 1 gram of chlorine. So we don't want 1 gram of each, we actually want equal amounts of atoms. So we could combine 1 mole of each, because that would be 6.02 times 10 to the 23 of each atom. And to do that, we would just weigh out a sample equal to its atomic mass. So then we would have sodium chloride, and it's not got the molar mass of sodium or a molar mass of chlorine. It'll have a molar mass of sodium chloride. And we just add up everything that's in there. And when we do this, you have to watch out for subscripts because they multiply things, right? So the molar mass of hydrogen is essentially 1 gram per mole because its atomic mass is 1. Molar mass of oxygen, 15.99 grams per mole. Okay. So if we make water, H2O, that's 2 hydrogens, because of this 2, plus 1 oxygen, that's an oxygen, which gets me 1 plus 1, or 2 times 1, plus 15.99. And so we get 17.99, and actually hydrogen's a little bit more than 1, so we usually just call this 18 grams per mole. Glucose, C6H12O6, would be a little bit different. Carbon is 12.01 grams per mole. Hydrogen, we're going to go with 1. Oxygen, we're going to go with 16. And so what we can do is we can take 6 times 12.01 plus 12 times 1 plus 6 times 16, and if we add that all up, we get the molar mass of one molecule of glucose. So 6 times 16 is 96 plus 12 plus 72.06, and we get our total molar mass. Now, how do we actually convert back and forth between atoms, grams, and moles? Well, it's just a unit conversion problem. Remember, 6.02 times 10 to the 23 times 10 to the 23 equals 1 mole. Okay, so that's whatever we need it to be. That's 6.02 times 10 to the 23 atoms, molecules, ions, whatever it is we need it to be. It's just a number. 1 mole is 6.02 times 10 to the 23. So let's say I wanted to have 5 moles of sulfur. Okay? Well, if I want 5 moles of sulfur, then I'm going to go find sulfur on the periodic table. And let's see, I have a periodic table. Let's pull that up. So sulfur is right over here. It's element number 16. It has a molar mass of 32.066. That's its atomic mass, so that's also its molar mass. So sulfur, 32.066 grams per mole. If I want the mass of 5 moles, if I was actually going to count out 5 moles of sulfur, that means I would actually weigh out some amount of mass. So I'm going to take 32.066 grams per mole times 5 moles. Right? Those moles cancel those moles, and that lets me calculate how many grams of sulfur I'm actually going to weigh out with my balance. And so 5 times 6 is 30, 5 times 6 is 30, carry the 3, 3, 0, 15, 16. About 160.33 grams, right, because that's the unit that's left, of sulfur. Now, how many atoms are actually in that? If I had 160.330 grams, or 5 moles, how many atoms of sulfur do I have? Well, to do that, I would say, well, 1 mole is 6.02 times 10 to the 23, so 6.02 times 10 to the 23 atoms per mole times 5 moles, and that gets me how many atoms I have, because those moles cancel, and that's going to be like 30.1 times 10 to the 23. So lots and lots of atoms. It's an incomprehensibly large number because atoms are so small.